Let me try this. Yeah, that's the one. Okay, good. Yeah, this is what I said. Okay, so it's all nice. But what about how do you design these for my application? So if you want to design a narrow band single frequency RC, it's very easy. You can get high directivity. Getting 15-20 dBi is not that hard. You can get good efficiency and good gain if you use low loss material. If you use something like FR for cheap, then you will not get good RF efficiency. Your RF efficiency could be 60%. If you use a high quality low loss dielectric like RT, Duroid, TMM, etc., you can get 90% or better RF efficiency. Designing multi-wideband and multi-band antennas are not so easy. So that's the one. That's what I'm going to explain today. You can't find a lot of tricks in design in papers. Them with circularly polarized ones. So let's see how. So there are two design methods. Now there are two types of resonant cavity antennas. One are large ones, right? One are large ones, and then small ones. Like small ones are 1.52 lambda naught. So these methods apply to larger ones. We approximate them by a periodic structure. When the antenna is very small, that approximation fails because it's so finite. Then you have to design and optimize in a different way. I will show you one optimization example later, but that's full wave. So these design methods are large antennas that has some sort of a periodic structure. We design unit cell first, then design the whole antenna, including the feed. And to design itself, we have two different methods. One is called transmission model, other one is reflection model. So what's the difference? I think I should go to the slideshow mode, the slideshow setup. Okay, that's better. One is transmission. So these are the two models. This is the reflection model, right? Remember, all resonant cavity antennas has a superstructure. This is a superstructure. In this case, superstructure has two dielectric slabs, but it doesn't matter. Any resonant cavity antenna, this is the superstructure. Okay. Forget about the example. And then the resonant cavity and the ground plane. So reflection model means you work out the reflection coefficient of your superstructure, looking from the bottom, because that's what the waves in the cavity would see. That's what it makes the cavity to resonate. Hence, that's why we call it a partially reflecting superstructure. Now, the second model. In the second model, we remove the ground plane and make an image of this superstructure. So we have the superstructure here, and then we have this height h, and then there's another image cavity, and then image superstructure, right? So it looks like this. This is a superstructure. This is the image of the superstructure, and this is double the height of this cavity. So this is h, This is 2 times h. In some cases, this h is lambda naught by 2, so 2 times h is approximately lambda naught. But that is not the case always. It's usually the case. Especially in this case, we assume that we are using PEC ground plane. In that case, this is about lambda naught. So we have 2 models. We can use either to design. Just work with the reflection model first. To achieve high directivity and high gain, we need to satisfy 2 conditions. One is the cavity resonance condition. The cavity has to resonate. And the second condition, the reflection from the not necessarily the EBG structure, any superstructure, reflection from the superstructure should be strong enough, right? It's a partially reflecting, but should be reasonably strongly reflecting. So the cavity resonance condition is this. That's the equation. What it says physically is, if you consider a wave that is being reflected and propagating between the 2 walls. On the top, it is the superstructure. In the bottom, it's a ground plane. That path length should be an integral of 2 pi. K is an integer times 2 pi. That will create the phase coherence. Okay. So if you think about a wave that is bounced back and forth between these walls, when it is reflected by the superstructure, it will experience a phase change in the wave, and that is determined by the phase of the gamma. So phi p is the superstrate phase, the reflection coefficient phase of the superstrate. So this gamma is a complex number, right? Its angle is phi p. And then it propagates down this distance of this distance of h. So h times, when a wave travels in the distance of h, it experiences a phase shift of 2 pi divided by lambda times h. So you get 2 pi divided by lambda times h, not 2h, when it travels down. Then it is reflected by the ground plane. And the ground plane has a reflection coefficient that is phi g, reflection coefficient of ground plane. Now, if it is a perfectly electric conductor or a good conductor, this angle phi g is 180 degrees or pi radians. So you can simply put pi here. Then it comes back along the same path upwards and experience another 2 pi divided by lambda times h phase delay. So altogether, one complete loop, the phase change is phi p plus phi g minus 2 pi over lambda times h, and that sum should be integer times 2 pi. And that is the cavity resonance condition. When this is satisfied at one frequency, the cavity would resonate. And if you want dual band antenna, this should be satisfied in both bands, and so on. Okay, so this is one condition. Effect of cavity resonance condition on gain. So we have already seen this. This is actually the gain variation of resonant cavity antenna. Here we are not changing the frequency, but changing the superstrate height, that h, where this h, because h is in this equation, right? Only for one value of h, this is satisfied, condition is satisfied. For other values of h, this condition is not strictly satisfied. And for that particular value, in this case h equals 12.8, the resonance condition is satisfied and you get the maximum gain at this frequency. If you increase the cavity height h or decrease the cavity height h, then the sum is not equal to that, so your gain would drop. Okay, so that's a demonstration. You can actually simulate a small antenna and see this by changing h. Now the reflection coefficient magnitude. I said the second condition is reflection from the EBG structure should be strong enough. That means this gamma magnitude, previous look at the phase of gamma, now we are looking at the magnitude of gamma, should be strong enough. So this is the gain variation of the antenna versus reflection coefficient magnitude. By changing the reflection coefficient magnitude, we can study the gain variation, and it becomes, in this case, you get maximum gain when the reflection coefficient magnitude is about minus 2 dB or minus 1 point something. So that is a quite good, not perfect reflector, of course, it's a partial reflector, but a good reflector. And this changes with the type of RCA. So why most of the early resonant cavity antennas, those days we were calling them electromagnetic band gap resonate antennas, that's why they EBG resonator. Why they are narrow band? They are narrow band because the reflection phase of most of the superstructures decrease with frequency. Okay, but to get wideband performance, we need a reflection phase that increases with frequency. So we don't satisfy the cavity resonance condition at all frequencies. It's satisfied only at this frequency. Only at this frequency. As soon as you change the frequency, you break the cavity resonance condition. Cavity would not resonate, and you lose directivity and gain, and you have a narrow band antenna. There's a paper by Prasad with all the theories about this cavity resonance condition. So to carry on, this is the kind of phase reflection coefficient phase of the superstructure we need to make a wideband antenna. It should increase linearly with frequency in a particular way. But a lot of superstructures behave like this. So how do you get this kind of phase from a superstructure, right? That was the question. This is the ideal one. This is the actual one with standard superstructures. So this is, I will show you a couple of ways of getting that. One way to get that is, this is a 2D FSS type superstructure, printed dipoles or slots. In this case, it has the superstructure is a dielectric slab with metal on both sides, but we etch slots on both sides. So it's a slot array, 2 slot arrays on the top surface and the bottom surface. So this is a unit cell. But these slopes are different. They have slightly different lengths, not the same length. We tune the slopes to two different frequencies. So slopes on one side resonate close to the lower end of the band of the antenna you want to operate, and those on the other side are tuned the upper end of the band you want to operate. By doing that, we can change the reflection phase versus frequency plot to increase with frequency in the band you want. So you can see the reflection phase versus frequency. In a normal partially reflecting surface or partially reflecting superstructure, it is like this. Reflection phase decreases with frequency. It's decreasing here, decreasing here. But you can see in this section, in this band of frequencies, it increases with frequency. Reflection phase increases with frequency from 11.6 to 12.2 gigahertz, leading to wideband gain in the antenna. And when you look at the reflection coefficient magnitude, which is S11 magnitude, you can see that it's greater than -4 in that frequency range. That is not very good reflection, but it's good enough. So you can make a wideband antenna that way. Now that is used in slots. Okay, so you have metal on both sides and you print out slots. Now this is the opposite of that, very similar but opposite, because here again we have a 2D periodic structure, frequency selective surface, printed PCB. That is our partially reflecting surface or the superstructure. We can call it a superstrate in this case because only one. And these are dipoles. So we have metal strips on one side and more metal strips on the other side, but with different lengths tuned to different frequencies. So this way we could get measured 3 dB gain bandwidth of 15.7%, effective bandwidth 12.6%, because the 3 dB gain bandwidth did not match with 10 dB return loss bandwidth, and peak gain 16.2 dBi, etc. So this kind of antennas can be designed to have wideband or dual band characteristics, because the phase of the reflection coefficient increases with frequency. It has a positive phase gradient. That's why if you see our paper, the name of that is, I don't know whether, yeah, this one. If you look at that, it says, in the name, the inversion of the reflection coefficient gradient. That's what we did. We changed it from negative to positive. So we can utilize this characteristic to design different surfaces and different antennas with different characteristics, with different parameters. Here you see 3 phase profiles of this surface, PRS1, PRS2, PRS3, and let's see how they perform. This is PRS3. Gain versus frequency and directivity versus frequency. So gain is very good in this case, peak gain but the bandwidth is not the best. Okay. That is because if you look at the PRS3 phase curve, so difficult to see. One, they're all broken lines. It doesn't have enough positive section, positive grading. Whereas the PRS2 has the long positive part, positive gradient. Because of that, that gives wide bandwidth. Gain bandwidth is the best in this case over larger range of frequencies, but gain itself is little less. Peak gain is only 16 dBi. Then PRS1 is actually a dual band antenna. It has good gain, reasonable gain here. The gain drops and it increases again. So that is because it meets the cavity resonance condition here and here, does not satisfy cavity resonance condition in the middle. So that is a summary how to design a dual band resonant cavity antenna. We need to design we have to design a partially reflecting surface with the phase that goes like this. Going down versus frequency and then jump or increase and then going down again. Because it radiates when the phase curve meets this ideal condition. This is the ideal condition, the black curve. A normal PRS have phase like this, so it's not going to work in two bands. But this green one, you can see the green one intersects the ideal line at two frequencies. It intersects here, it intersects here. So if you can synthesize a surface, partially reflecting surface that has its reflection phase, this is the phase value of S11, that's the same as gamma I showed you before. It will radiate at this frequency, it will radiate also at this frequency. The superstrate reflection phase should meet the ideal curve at least two frequencies. For that, you need sharp inversion of the gradient, and also the reflection coefficient magnitude should be sufficiently large at this frequency and this frequency. So that's what happened in this design. These are again slots. Unit cell is this with the slots. And the reflection phase of that surface slot array, actually it has two slots printed. Actually, so this one is actually only one slot, printed resonance slots printed only on the lower surface. So because of the resonance, because of the slot resonance, its phase jumps here, right? The phase jumps here. And now when you look at the resonance condition, when you look at the resonance condition, it meets the resonance condition at this frequency and this frequency and also at this frequency, right? So you think it might radiate at all three frequencies. But it turned out that it does not radiate well at this frequency, but it only radiates well at this frequency and this frequency. So what you get is dual band antenna. Cavity formed by the normal PRS, red one, resonates only at one frequency, but leading a single band antenna. Cavity formed by the new green PRS can potentially resonate at three frequencies, but it's not actually a triple band antenna. It's actually a dual band antenna. It radiates well here, radiates well here. It doesn't radiate well here. Why? Why it does not radiate at that frequency? That is because the magnitude of the reflection coefficient. Partial reflecting surface reflection magnitude S11 is too small. So the surface is not reflecting enough. It's actually a transparent surface at that frequency. So it cannot make the cavity to resonate at 12.1 gigahertz. So that cavity does not radiate, it's not a good antenna, but it's a good antenna at the other two frequencies, where the reflection magnitude is large enough. So around 11 gigahertz and 13 gigahertz cavity resolution is satisfied, and reflection magnitude is large enough. So we meet both conditions necessary to operate like a resonant cavity antenna, and you get a dual band antenna. So also remember, FSS resonance is not the same as cavity resonance. In this FSS or the PRS resonates only at one frequency here, right? That's the PRS frequency. That's the resonance of the slots in the surface. But the cavity does not cavity resonates here and here. So these are the cavity resonances. Cavity resonances are determined by the cavity resonance condition. The surface internal resonances are determined by the slots, the resonance frequency of the slots in the slot array. Okay, so there are other ways to explain. You can read the papers, I think, because we have to move on. There are several papers we published. Some have a lot of details. So create the PRS. This is an interesting feed. You can see it's a printed strip. It's not a microstrip patch, it's a printed strip with a coaxial feed. So it's not on the ground plane, it's lifted a little bit above the ground plane. And that has very good coupling to the resonant cavity. So making a dual band antenna, you can see radiates at two frequency bands, get good gain at 11.27 and 13.4. Measured reflection loss, return loss. It's not really return loss, reflection coefficient magnitude is good at these frequencies. Measured radiation patterns, etc. This is another design for the two 5 gigahertz Wi-Fi WLAN frequencies around 5.2 and 5.8. Some of the parameters. It has directivity and better directivity at the higher band, less directivity at the lower band, and so on. Okay, so I think that is how you use this method, the reflection coefficient, to design the partially reflecting surface and the cavity. This is another example. You look at the reflection coefficient and it goes up and down, and it works at this frequency and this frequency, where reflection phase intersects the ideal phase. The resonances and the dual band, again, it does not radiate well at this frequency because of the small reflection magnitude. The other two bands you get good directivity, dual band antenna. If you use TMM10 or high quality low loss material with the high dielectric constant, you get more directivity and also gain very close to the directivity. If you use low dielectric material like FR4, your directivity is less, but because these are lossy, efficiency is even less, the gain is even less than the directivity because of the material loss. TMM10 has very small loss, almost negligible. So this is a comparison between high TMM10 and FR4 designs. Some of our FR4 designs that you saw before, the dual band. You saw this before, remember? That's a dual band. So we designed the cavity to resonate at two bands. And as I said before, you have stack patch antenna to feed the two bands. So these are the patterns in the two bands of that antenna. And the gain, measured gain of the two antennas. You can feed the antenna with a small array instead of one or two elements. So we have done that too. So you can get better performance. And so that is basically how to use the reflection model to design resonant cavity antennas. Now I will switch to the other slides where to explain how you can use the other model, that is the transmission model. The transmission model to design resonant cavity antennas. I guess I got the right slide. Yeah, looks good. Okay, using the transmission model. Oops. No, that's not the right one. This is the right one. Okay, stop to center. Yeah, that's the one. So hide that. Okay, so now we are going to study this model, right? The superstructure and its image and the cavity, double-sized cavity. How can you use this to design? The first, I assume that the superstructure has multiple layers, like those 1D electromagnetic band gap structures, like this one. So 1D EBG resonator antennas with multiple dielectric slabs can be designed this way. Actually, any of them can be designed this way. any of those resonant cavity antennas. But this one is particularly interesting because you can derive analytical theories. You can analyze it analytically, even if you don't have the software to analyze. So this is 1D electromagnetic band gap material. 1D means, so these are very large, infinitely large dielectric slabs, infinite in X and Y direction, and stacked, same material, same thickness, same spacing stacked to create a 1D electromagnetic band gap. 1D means it can stop wave propagating in Z direction. If you had enough slabs, it will block propagation completely in the Z direction. But it does not have the band gap in other directions, along X, Y direction, Z direction, etc. So it does not have complete band gap. The photonic crystal, the wood pile you saw in the previous lectures, have complete band gap. Okay, so that's the base 3D band gap. This is only 1D. Okay, now what happens if I remove one slab? Remove one slab. And now this is a defect. Remember in this theory we discussed in the wood piles, we discussed when you remove one rod, it becomes a defect. And this is also a defect. So you have dielectric slabs and a defect. Now this is exactly what we have in our model, right? In our transmission line model. We have several slabs, that is the superstructure, and its image, and then double the cavity, and that is a defect. So we can analyze this using EBG theory. And this theory is even older than EBG. This is how in optics they came up with the Fabry-Perot resonance and Fabry-Perot cavities in optics. So hence these are called Fabry-Perot antennas, especially the 1D type with multiple dielectric slabs. So Fabry-Perot is a good name for resonant cavity antennas with multiple dielectric slabs for this reason. So it has the Fabry-Perot resonance. But some people call all type of resonant cavity antennas Fabry-Perot, although it has very little to do with Fabry-Perot. Yes, what is the question? You can ask now. Nasima, do you have a question? We can't hear you. Can you say it loudly? Can you say it loudly?
I think wrongly she raised some hand, maybe.
Yes, it's not coming through. If you can, just type in your question to the chat. Now, I will not go through the theories. I will give you the handouts of these slides, right? The PDF, so you can read the theories and understand, because we are running out of time. Dielectric multilayer theory. From this theory, you can work out the transmission through the surface. The reflectance, what is the reflectance of this surface, what's the transmission of this surface? These equations have been used by optical people in optics for a long time, but we can also use it for antennas, RF, because optics also optical waves are electromagnetic waves. Now, how can you make use of that EBG? When you design an antenna, so we build this model, okay, and we calculate transmission through this. Transmission, you can build this like a unit cell in CSTO and CIS and analyze transmission through this unit cell, you assume in unit cell boundary conditions and normal transmission, and you can plot the transmission and reflection of that unit cell. If you don't have a defect, that means if you simulate something like this, as I said before, it has band gap in Z direction. So your transmission curve looks like this. This is transmission in dB. Transmission is reasonable at low frequencies, reasonable at high frequencies, but with this band, transmission is very small. So that is the 1D band gap. Okay, so that's a 1D band gap of this EBG structure, or if you want to call it a photonic crystal. So that is this dotted curve. Now what happens if you have a defect like this? Cavity, double the cavity is a defect. When you introduce that defect, you see a defect mode within the band gap. At some frequencies giving good transmission again, so this defect mode introduces a pass band, in this case at 12.118 gigahertz. This defect mode is due to the resonance of the defect cavity. We can use this defect mode to make a high gain antenna operating at that frequency. So if now what we have done is we have designed cavity size for an antenna that radiates at 12.118 gigahertz. But also you can see that this defect mode is very narrow, right? Happen only at that frequency. If you increase the frequency a little bit or decrease, there's no defect mode. So this antenna you make this way is very narrow band. It's going to be very narrow band. So there are a lot of slides here about oblique incidence, etc. These are similar to what I discussed previously on frequency selective surfaces, oblique incidence. So I will skip those and get to the just cavity resonator antennas. So how do we make an antenna out of that? We already found this superstructure, right? We already designed the superstructure. We worked out the cavity height. We know the resonance frequency. Now we go back to the model that has a ground plane and the feed. All you need is a feed. So you can design a patch or any other feed that works at this frequency to excite the cavity. And then it works. So this is the input reflection magnitude of the antenna. You can see it resonates very well, has a good reflection coefficient less than -10 in this band around that frequency, but it's very, very narrow band, 0.53% around that resonance frequency, and you get good gain. So we predicted resonance frequency, predicted bandwidth is this, the actual measured bandwidth is this. And the radiation patterns, etc. So I will These are the measured directivity and gain versus frequency. So this was one of the very early 1D EBG resonator antennas. Still has reasonable, okay, the measured performance, and then about increase in the size, aperture size. We made it 6 lambda naught by 6 lambda dot. Increasing it further would not give us much directivity, actually directivity drops. And these
can we
large
have
antennas, when we decrease the size, also directivity drops. So this is quite different to the other type of antennas you saw before, the smaller ones, where when you make it smaller, the directivity is still good. Okay, it's just some pattern plots, etc. Now, if you want to get better bandwidth, this is one way to do it. I think I mentioned this before too. You can feed the cavity using a slot array. This is quite tedious to design because you have to feed all these slots, and we had to design, I think, a slot what is it, strip line distribution system to feed all 32 slots, but it gave good performance. Now this is the defect model of that. You can see this is the defect mode. Now this is wider. This was the previous defect mode, and this is the new defect mode. How did we get that? We got that by changing spacing, optimizing the spacing between these dielectric slabs, and also using different material. These two are TMM4, this is TMM3. They have different dielectric constants. The gaps are different. This is 5.5, this is 12.7. So the superstructure itself became like dual, has dual gaps. And when we analyze this using the transmission line model, you can optimize the superstructure using the transmission line model. If the defect mode is narrow like this, you get very narrow bandwidth. If the defects mode is wide like this, you get very wide, or at least better bandwidth from the antenna. So you can see the defect mode bandwidth increased from 0.54% to 9% in this case, due to the optimization of the slabs and slab spacing. So that is this antenna with TMM material, with optimized slab material and the gaps. And its input reflection coefficient less than minus dB here, measured gain, etc. Measured patterns. Okay, so are there any questions about the design, the two design methods of this type of antennas, the reflection coefficient method and the transmission model method? Because if not, I will switch to another topic, the last topic on resonant cavity antennas, that is about optimizing. How do you optimize these antennas, especially those that are small? right? Especially those that are small. Because those two methods we just discussed, they apply only to large antennas. So the optimization methods I am going to present now, if I can find the window. Give me a second to find the right. This. Okay, it should be here. Yeah. Okay, optimization of resonant cavity antennas. We have applied three optimization methods to optimize. Actually, this has another antenna that was designed using the waveguide model that has very wide bandwidth, that use a wideband antenna. But let's talk about the optimization now. Here are several methods used for optimization in our field, antenna and electromagnetics. We haven't used all the methods. We have used genetic algorithm AI. We have applied particle swarm optimization PSO, and also we could not do what we wanted to do using all these methods. So we were looking for new methods, and we found another method used in other areas like mechanical engineering, not used much in electromagnetics and antennas, cost entropy method, and we applied that and published few papers. It has very good quality, very good, very advantages. It can do things the other methods cannot do. So our genetic algorithm application is here. Here we are trying to optimize the printed pattern of a FSS type resonant cavity antenna, right? We're trying to optimize the metal pattern on both sides, independent. So they have independent patterns. So for this one, we actually got the genetic algorithm to try different patterns and come up with the best pattern. So this is the pattern it came up. This dark part means metal, white means you etch the metal on the FSS. So this is double-sided frequency selective surface with metal on both sides. This is a unit cell for the upper surface, and then for the bottom side, the lower surface, this is the pattern, and this is the unit cell. We have done this research with Yang Hao, etc., in University of London, and we published it together. So that is not a lot of things, but then that is a large antenna with periodic structure, right? Then we were designing smaller resonant cavity antennas. We have to optimize the whole antenna because there's no unit cell. Unit cell method doesn't work. because the antenna itself is very small, one lambda node, 2 lambda node. So we were looking for other methods. Particle swarm PSO is probably the most popular in antenna optimization. You probably know the basics, so I don't have much time to go through the basic PSO. You have particle swarms representing the variables, and you let them try different values. So at that time, PSO implementation in CST was not very good. Now it is much better. Although CST has, I think, better optimizers than PSO right now. But those days it was horrible, so we had to write our own PSO code in MATLAB, and we interfaced that with CST to automate the optimization. So CST does the computation, gives the output to MATLAB. MATLAB analyzes the result, the objective function, check whether we met the criteria, we got the solution. If not, it will go back to the optimization PSO algorithm in MATLAB, decide the next set of variables, and then give it to CST to calculate. And this is automatic, right? We don't have to, we can just let it run iteratively until it meets the criteria. So we optimize a lot of antennas this way. This is the TPG type antenna we optimize using our PSO. And there are a lot of results here. It gave us several solutions at the end. These are the values. You probably noticed that it has 4 different dielectrics in the design. 1, 2, 3, 4 dielectric material, and we were optimizing their parameters, basically the dielectric constant values. So these are the various solutions it gave us, and some of them are very similar with dielectric constant. The first one and second one is 10, the next one 6.7, the next one is 3.3. That's very interesting. Remember, by theory, from physics, that is how I ask my students to design TPGs, superstrates, put highest dielectric constants in the center and decrease towards the edges. And the PSO does not know any physics, but at the end, after doing this iteratively, it came up with solutions very much like that, decreasing dielectric constant with radius. So we got these parameters, and this is our best PSO optimization done by my students and postdocs, published in IEEE Transactions, and this was not easy. We wanted to get better than 20 dBi gain from a resonant cavity antenna with wide bandwidth. So we had to do some clever things. Some of them obvious. We had to use 4 dielectrics instead of the 3 in our original design. We had to make it a little bit larger. Now it is 5.3 square wavelengths, and we have to make the thickness variable. As you can see, the thickness of the dielectric in each section is optimized. It's not totally flat. It's not totally planar. There are steps. Otherwise, it's very similar. Resonant cavity is air field, actually form field to support the superstructure. and the ground plane is the same area, has the same area as the superstructure. So we met what we wanted to do. We got very good bandwidth, gain bandwidth of 57%. Peak gain get better than 20 dBi. And those are the computed, and then so these are still computed, the side lobes, etc. And then we fabricated and tested. So the measured directivity, measured matching, and gain bandwidth product per unit area. Now, I said before, resonant cavity antennas got the very high gain bandwidth product per unit area. This is our first design, TPG type, that has 1300 gain bandwidth product per unit area. These are all scalable, unitless, and gain bandwidth product of 2012. This particular design, we want to increase gain bandwidth product, so we got almost 6000 gain bandwidth product with better bandwidth than the previous one, 57% bandwidth, better gain, of course, excellent gain, but gain bandwidth product per unit area dropped because we have to increase the area to get gain. So I think I promised to say a few things about the lens antennas, because a lot of people get confused between resonant cavity antennas and lens antennas because they look like lenses, right? But they are quite different. This looks like a lens, but it is not a lens because this one reflects. The lenses are not supposed to reflect. Lenses got to be transparent, right? But this reflects. So resonant cavity antennas need a ground plane and need this cavity resonance between the two. But lens antennas don't need that. As a result, lens antennas are usually bigger and taller. So the first four in this one are resonant cavity antennas. The last four are lens antennas, including some flat lenses. You can see the difference in area. These resonant cavity antennas are much smaller. This one is large, but the newer ones are very small, have very small area, very small height in terms of wavelengths, usually 1 lambda naught or smaller, whereas lenses could be very long, including the feed and the gap between the feed horn and the lens. 10 lambda naught could be 10, 5 or so on. Area could be very large. But lenses can give you very high gain and directivity, more than resonant cavity antennas. So resonant antennas saturate about 25 dBi or so. With lenses, you can get 30 plus. Bandwidth also, you can get better bandwidth if you want. So if you have a volume, if you can have very high height and area, then you can get better performance using lenses. But if you have limited height and area, limited volume, the resonance cavity antennas are much better. So when you divide the directivity bandwidth product or gain bandwidth product by area to make it unitless, you can see good resonant cavity antennas got gain bandwidth products or directivity bandwidth products well above 1000, and lens antennas are much less. So that's the biggest difference in performance between these two types of antennas. They are not competitive, they are more like complementary, depending on the application. Okay, so Yes, some of the references, but you can find a lot more in my papers. Simply go to, you can Google my name and the type of antenna you want. Now, I remember one question I answered today about whether there are TPG antennas with various materials like carbon nanotube, etc. I don't know, but you had to do your own literature search and Google search, or I explore, IEEE explore search. But there's one thing very important to remember, because different people call these different names for these antennas. You have to search with all different names. Right? Remember all the names I mentioned in the beginning. So, for example, if you want to find a, I know some people design flexible antennas, wearable antennas that have this principle of operation. So, if you want to find whether anyone done with the carbon nanotube and this kind of antennas, you have to search carbon nanotube and resonant cavity antennas, carbon nanotube and Fabry-Perot resonate, Fabry-Perot antenna, carbon nanotube and EBG resonate, and so on. So you have to do several keyword searches to find all the antennas, because people use different names. If you, I know some people just did only one search and wrote papers and found that someone else did exactly more or less the same thing, but gave a different name. And when you, if you do that, when you try to publish, it will be a problem. When you try to defend your thesis, it could be a problem, because your examiner or the referee would find that someone else has done and you haven't done proper search with all the keywords, and only search, for example, Fabry-Perot, but those people called it something else. Same with the other surfaces. Sometimes some people call them transmit arrays, some people call it metasurfaces, some people call it FSS, frequency selective surfaces, some people call them meta lenses, some people call them deflectors, right? There's a lot of names depending on the application. Some are based on application, some are based on physics. There are a lot of names for the same thing. So be careful when you're searching, search thorough, search all the relevant words. Well, another question I answered was, like, is FSS is the right word, the metasurface is the right word, because some people use, so the best thing is to use the word others have been used. If the other people, for example, for the radomes, for radars, etc., frequency selective surfaces, normally FSS is the word used, so it's best thing to use that instead of a metasurface. I remember in one of the major conferences, I think European Conference on Antennas and Propagation last year in, where was it? It was in Lisbon, Portugal. The keynote speaker was talking about FSS, and someone asked a question about metasurface or something. The keynote speaker got really angry. He did not want to call it metasurface, he wanted to call it FSS. So you can run into issues if you try to call the same thing by a different name. Best thing is no need to invent names, just invent better devices, right? If some people call the same thing FSS, others call it metasurface, then that's fine. You can pick whatever you like. But if everyone else call it FSS, better call it FSS, not meta something. Okay, so it's still that, like, so from tomorrow we have two lectures and we will be talking about metasurfaces, near field phase transformation, and MetaSteering, beam steering. Okay. So we start from here. So before we stop today, are there any questions? We have 2-3 minutes.
Participants, if you are having some queries, you can ask.
Okay, you're all welcome. So I Saurabh, you got my email, right, about tomorrow?
Yes, sir.
Uh,
I got
I
your
think
email. We will
yeah.
be
So
prepared accordingly.
okay.
So
I
we
should
can
be
have,
able to finish the formal lecture in the first 2 hours.
yeah,
The uh, phase transformation, near field phase transformation, near field phase correction, and near field meta steering. Um, then we can start the discussion. I think the discussion part will be open to other people as well, right?
yeah.
Okay.
We can have from 2 to 2:30. We can have the discussion, and then we can have the validatory session after that.
Just let me check the schedule. Lecture 12 and 13.
Yeah, we
Because
are.
we are running behind, that will be all about near field meta steering.
Mhm.
I guess. Yeah, I should be finished by about 2 for the
Okay.
discussion.
Yeah. As your lecture session 2 will be from 5:45 to 6:45. You can extend it
Yes,
if you want till 7:30. And after from 7:30 we can have the discussion over the interaction means,
I
I
will
can say.
not be, I will not be able to talk that long
Okay.
continuously. So we'll take a break like today,
Yeah.
6:45, and then
Okay.
come back for the come back for the discussion at 7:30, unless if
Mhm.
you want to start this discussion at 6:45 and finish early.
As you want, sir. We can reschedule if you want
Is it
that we
okay?
can.
Is it okay with the others in the faculty, other people coming?
So actually, here in the NIT, we are having the three faculties. One is Dr. Chandra, I, and Dr. Amit Bage. We are having the three faculties with this particular research area.
Okay. Okay, then because I can stop my lecture at 6:45.
Okay.
So instead of taking a break of 45 minutes,
Okay.
let's do the discussion in that 45 minutes,
Okay. And then
45
from
or 1 hour.
okay, and then from 2 we can have the closing.
Yeah,
Okay, then I will reschedule the thing and accordingly.
yeah, from 2 we can, I don't think closing ceremony will be long, right?
It will be of 5 to 10 minutes. Just we have
Yeah,
to take the participants'
okay.
feedback, some feedback,
Yeah,
and your feedback we will be taking through the form that is shared by the GIAN.
right. That is good because I have to go for a dinner tomorrow too.
Yeah.
So that way I can finish around 7:30.
Okay.
Otherwise, I'm going to be late for that dinner.
Okay. We will be trying to finish it very early as per your requirement. We will be finishing within the 10 minutes, around 10
Yeah,
to 15 minutes.
Okay, so instead of the break, we will continue after my lecture, the discussion, and then try to finish.
We will be representing that what are the research going on in the our group, and then
Okay, okay,
we can have the discussion with you,
okay,
and then we will be starting with the closing ceremony.
okay. Thank you.
Thank you, sir.
See you tomorrow. Bye bye.
Bye bye, sir. So thank you so much for the today, all the participants. We are just